This is your presenter Asloob Mudassar, and I am presenting slide number 59 of the course on laser physics. Question is, discuss the saturation behavior of the absorption coefficient assuming a homogeneous line absorption when the saturating beam is a continuous electromagnetic wave. The second case is when the saturating beam is a light pulse. The answer is, to see how the shape of an absorption line changes with the intensity of the input beam, consider an idealized experiment. A probe beam of variable frequency nu prime and the intensity I prime of nu prime illuminates the material collinearly along with the saturating beam of intensity I of nu, and the absorption measurement are made. The probe beam illuminates and interacts with only the saturated region of the material. I prime of nu prime is assumed to be small enough not to perturb the system appreciably. The absorption coefficient seen by the probe beam in terms of the homogeneous line shape G of nu prime minus nu naught when saturating beam is absent is given by. So the absorption coefficient in the absence of the saturating beam is given by alpha naught, where alpha naught is equal to 2 pi square over 3 n epsilon naught Ch multiplied by the absolute square of mu multiplied by nt multiplied by nu prime and then multiplied by G of nu prime minus nu naught as given in equation number 59.1, where nt is equal to n1 plus n2 is the total power, is the total population present in the level number 1 and level number 2 per unit volume. In the presence of the saturating beam, the absorption coefficient according to equation number 42.2 is given by. So this becomes then the absorption coefficient in the presence of the saturating beam, and we have alpha is equal to 2 pi square over 3 n epsilon naught Ch multiplied in the numerator by absolute square of mu multiplied by delta n, which is the difference of a population and the frequency of the beam, and then Gt of nu minus nu naught, where delta n is equal to n1 minus n2. The equation number 59.1 and equation number 59.2 can be expressed using equation number 58.9 as this. That is, alpha is equal to alpha naught over 1 plus I over Is. So we have presented equation 42.2 and the equation number 58.9 in the appendix, and let me show you these two equations. For example, this equation number 42.2, where we have given the value of the absorption coefficient alpha, and we have replaced in our case n1 minus n2 by delta n. The rest of the quantities are the same. And equation number 58.9 is delta n, the ratio of the difference of a population to the total population, delta n over capital delta n over nt is equal to 1 over 1 plus I over Is, where I is the intensity of the saturating beam and Is is the saturation intensity. For the details of these intensities, you can consult slide number 58. So you see that if we compute, since we have alpha naught over here in equation number 59.1 and alpha present over here, so computing the ratio of these two quantities, we have alpha over alpha is equal to alpha naught over 1 plus I over Is, where you see that we have replaced delta n over nt by 1 over 1 plus I over Is, as just shown, as I have just shown you the equation number 58.9. So using that equation, this one delta n over nt has been replaced by this factor on the right hand side, which is 1 over 1 plus I over Is. So here we have made use of the three equations, that is we have used equation number 59.1, equation number 59.2 and the equation number 58.9, and we have written this, that is alpha is equal to alpha naught over 1 plus I over IS, where you know that alpha naught is the absorption coefficient in the absence of the saturating beam, and alpha is the absorption coefficient when the saturating beam along with the probe beam, both beams are present. So this is what we have written, the relationship between the two absorption coefficients as given in equation number 3. Using g of nu prime minus nu naught from equation number 36.15. So let me show you this equation. This one, g of nu prime minus nu naught is equal to 2 over pi into delta nu naught multiplied by 1 over 1 plus square of 2 into nu prime minus nu naught divided by delta nu naught. This is equation number 36.15. For the detail, you should consult slide number 36. So using g of nu prime minus nu naught from equation number 36.15 and using alpha naught from equation number 59.1 and alpha from equation 59.3, we can write equation number 59.3 in the following form, that is this equation, alpha is equal to alpha naught over 1 plus I over IS can be written as alpha is equal to this expression on the right hand side. So you see that we have this expression, we have the total population NT is present in this expression, and 1 plus I over IS is also present in the denominator of NT, and the rest of the quantities comes from g of nu prime minus nu naught as from equation number 36.15. So this full expression of the absorption coefficient in the presence of both the beams, that is the saturating beam and the probe beam, we have the absorption coefficient given by equation number 4. Now ignoring the constant terms, we can write that alpha is proportional to 1 over 1 plus I over IS multiplied by 1 over delta nu naught and then multiplied with nu prime over 1 plus square of 2 into nu prime minus nu naught divided by delta nu naught. So alpha is proportional to this quantity. The rest of the quantities which were constant has been ignored. Now the plot of saturation behavior of the absorption coefficient alpha. So you see that now this alpha is may be referred to as the behavior of this alpha may be referred to as the saturation behavior. So the saturation behavior of the absorption coefficient alpha for the case of homogeneous line shape versus frequency nu prime, assuming arbitrary values for nu naught and delta nu naught, and for increasing values of the beam intensity is shown in figure number 59.1. So the plot is shown over here. We have plotted alpha, the absorption coefficient along the vertical axis. We have plotted the frequency nu prime, which is the frequency of the probe beam, on the horizontal axis. We have assigned arbitrary values to the resonant frequency nu naught, and the caption is a plot of absorption coefficient versus the frequency of the incident probe beam. And you see that we have set different values of the saturating beam. In the first plot we have set the zero value for the saturating beam. That's why we have I over IS is equal to 0. Here I is the intensity of the saturating beam is 0, and you can see the absorption cross section. So it attains the highest value when nu prime is equal to nu naught. So the value is the highest, and you see that when nu prime deviates from the resonant frequency nu naught, you can see that how symmetrically the value of the alpha falls on both sides. Now when you increase the value of the saturating beam such that the saturating beam is the same as the saturation intensity, then you have I over Is is equal to 1. And in that case you can see that the absorption coefficient alpha has fallen drastically. So the maximum value is at nu naught. So when the probe beam frequency nu prime is deviating from the central frequency nu naught, then you can see that the absorption coefficient also deviates, also falls to nearly zero, also falls to 0 on both sides. And the third case is when the intensity of the saturating beam is actually 9 times of the saturation intensity. That is I over Is is equal to 9. Under that condition, you can see that the absorption coefficient alpha has fallen drastically, and the value of the absorption coefficient is shown in the third plot, which is very small in amplitude. And the maximum value is again at nu is equal to nu, at nu prime is equal to nu naught. So when the frequency of the probe beam nu prime deviates from the resonant frequency nu naught, you can see that the fall in the absorption coefficient. So actually this is the behavior of the absorption coefficient under a homogeneous line shape. And let's go back to the question. Discuss the saturation behavior of the absorption coefficient assuming homogeneous line absorption when the saturating beam is a continuous electromagnetic wave. So we have given the answer for up to the when the saturating beam is a continuous electromagnetic wave. So the part 1 has been addressed. Now we have to address the part number B, in which our saturating beam is a light pulse. So now we consider the case when the saturating electromagnetic continuous wave is replaced by a light pulse represented by I as a function of t, that is I is equal to I of t. Because for a pulse we have to define I is equal to I of t, because the intensity is not constant but varying with time. Now there are two possible cases that we can discuss. So two cases arise. The case A is pulse duration is very long compared to the upper state lifetime tau. So here we are saying that tau is the upper state lifetime under spontaneous emission of the upper state level, that is level number 2, and our pulse duration is very long compared with the value of tau, with the upper state lifetime tau. So it means that the upper state lifetime tau is very short in comparison with the pulse duration. And the second case is when the pulse duration is much shorter than the upper state lifetime tau. In the first case, so let's first address the first case. In the first case, the time evolution of the resulting population difference delta n occurs at a very slow rate. And delta n, you know, that is n1 minus n2. So this occurs at a very slow rate because over time of the lifetime of the upper state level is very short in comparison with the pulse duration. And in that case we can write that the rate of change in delta n with time is much smaller than in comparison with nt over tau. And in this case we can literally set dn over d of delta n over dt literally equal to 0. So let me show you the equation from where we have taken this, from the appendix. So you see that, look at the differential equation given in equation number 58.2. So look at this equation. So you see that if you bring nt over tau on the left hand side, that is on the term on the left hand side of the term, the term is d delta n over dt, and this term is much smaller than in comparison with the nt over tau, so this term can be ignored. And when this term is ignored, it means that we can set this term equal to 0, and then we can solve rest of the parameters from this equation. and from equation number 58.2 and from equation number 58.9 I have shown you the equation, these two equations from the appendix 58.2 and 58.9. These are the equations from the appendix. This is the 58.2, which is the differential equation, and this is 58.9, which is the delta n over nt is equal to 1 over 1 plus I over is. So if you set delta n, if you set the derivative of delta n with respect to time equal to 0, you will get this equation. Delta n over nt is equal to 1 over 1 plus I over is. So that is the ratio of the difference of a population to the total population is equal to 1 over 1 plus intensity ratio of the intensity of the saturating beam to the intensity of the intensity at saturation. So here this I is actually the intensity of the pulse, that is I as a function of it. The saturation behavior is generally the same for a continuous electromagnetic wave, because we have obtained the same relation for the continuous electromagnetic wave, and this is the relation that we have also obtained same as that of the continuous electromagnetic wave. But you see that this relation was obtained when it was assumed that the pulse duration is very long compared to the upper state lifetime tau. So this case is the same as that of the continuous electromagnetic wave case. In the second case, what was the second case? The second case is when the pulse duration is much shorter than tau. That is, tau is much larger. So in the second case, the stimulated emission term 2W multiplied by delta n dominates the spontaneous decay rate given by nt minus delta n over tau. That is, nt minus delta n over tau is much less than 2W into delta n. Because here you see that in the second case tau is much larger in comparison with the pulse duration. The pulse duration is shorter, much shorter than tau, or equivalently tau is much larger than the pulse duration. So under that condition t is much larger, so we can set nt minus delta n over tau is less than 2W into delta n. The 2W delta n is actually the term corresponding to the stimulated emission process, and this nt minus delta n over tau is the term corresponding to the spontaneous decay process. Let me explain these two terms using an equation 58.2 from the appendix. That is this term. So you see that if I multiplied in this in equation number 58.2, if I multiplied by delta n inside the parenthesis, I have a minus delta n over tau and then minus 2W into delta n. So I can combine the two, 1 over tau terms can be combined. So I have nt minus delta n over tau becomes the spontaneous emission term, and the term which is minus delta n into 2W will be the stimulated emission term. This negative term, which is a spontaneous emission term, under that term this delta n will, the rate of change of delta n with time will decrease because of the negative sign present with the term which is minus 2W multiplied by delta n. And the other term is we have also a negative sign, but we have combined this negative sign over here, that is nt minus delta n over tau. This is the spontaneous emission term in which t is very large, so this term is actually very small. So under that condition, we can ignore the spontaneous emission term and we are left only with the stimulated emission term. So we have the rate of change of delta n with time, that is d of delta n over dt is equal to minus 2W into delta n. The third term which I have just shown, which is the spontaneously initiated term can be ignored. And this can be set equal to minus W can be set substituting the value of W, which is equal to 2 into sigma into I of t over h nu multiplied by delta n. Delta n is there outside the parenthesis, and the term in the parenthesis is actually the value of W, which we have obtained from equation number 58.6. So let me show you equation number 58.6 from the appendix over here. So you see that I is equal to W over W into h nu over sigma. So you can take the value of W, you can multiply I into sigma and can divide it with h nu. So you have written over here, and the 2 factor of 2 is coming from over here with 2W. So I have written this. Now this is the differential equation in delta n, where W was replaced using equation number 58.6, which I have just shown you. Under the initial condition, which is delta n at time t is equal to 0 is equal to nt, and delta n is equal to n1 minus n2, which means that under the initial condition the population of the upper state level is 0 and the whole population was present in the ground state or the lower state. So delta n at time t is equal to 0 is equal to the total population nt. The solution under this initial condition, the solution of the differential equation shown in equation number 59.6 becomes equal to as shown in equation number 7, that is delta n as a function of t is equal to nt multiplied by e to the power minus 2 sigma over h nu and multiplied by the integral from 0 to t I of t dt. Now we can identify some terms over here and we can write this in other forms. For example, the integral from 0 to t of I of t dt may be identified as the fluence of the pulsed beam. And the fluence mean, so let me read the text. To give a more physical form to the solution, we define fluence gamma of t. So we can represent this integral by gamma of t. And fluence, you know, that is the energy absorbed by the material per unit area from the pulse. So this fluence is the term used with the pulses of the laser beam, with the pulses or with the light pulses. And the energy absorbed by the material from the light pulses per unit area is called fluence. So fluence is, we are defining the fluence as gamma of t, and we shall replace the integral shown over here in equation number 7 by gamma of t. And we are also introducing saturation fluence gamma s in the following form. So we have gamma of t as the integral from 0 to t I of t dt, where I of t is the intensity of the impulse at time t. And then we have gamma of s, which is the saturation fluence defined as h nu over 2 sigma. So using these two expressions, we can rewrite equation number 7 in the following form as given in equation number 8 in terms of the fluence parameters. So delta n as a function of time is equal to nt multiplied by e to the power minus gamma of t over gamma s. The saturation behavior is thus determined by the energy fluence rather than by the beam intensity. Let us define delta n infinity and gamma t as the population difference left in the material and the total energy fluence of the light pulse respectively after the pulse has passed. Replacing the relevant quantities in equation number 59.8, we get delta n infinity is equal to nt into e to the power minus gamma t over gamma s. And I have defined delta n infinity and gamma t as the population difference left in the material and also as the total energy fluence of the light pulse respectively after the pulse has passed. So we have redefined equation number 8 as equation number 9 in terms of gamma t and gamma s. So if we multiply both sides of this equation by the term I have shown, which is 2 pi square over 3 n epsilon naught ch, and in the numerator we are multiplying it with the absolute square of mu, and then mu, and then gt of nu minus nu naught. And if we multiply this term on both sides of equation number 9, the saturation absorption coefficient alpha of the material for a light pulse, either long or short, compared with tau, is related to the unsaturated absorption coefficient alpha through the relationship. So if you multiply this term on the left hand side, then the left hand side can be written as alpha. And if you multiply this term on the right hand side, you know that on the left hand side we have the difference of populations, and when the difference of a population is present, we can define alpha, and when the total population is present, we can define it as alpha naught. So we have alpha is equal to alpha naught e to the power minus gamma t over gamma s. We have already defined alpha and alpha naught previously, that is in these slides. That is, we have defined, you see that this is the value of alpha defined over here, or you can see that alpha has been defined in equation number 2 and alpha naught has been defined in equation number 1. Alpha naught has a definition with nt as the total population, and alpha has the definition with delta n as the population difference, which is n1 minus n2. So using these definitions, we have obtained alpha is equal to alpha naught e to the power minus gamma t over gamma s. And from equation number 59.9, that is from this equation, if you compare this equation with this equation, you can write that e to the power minus gamma t over gamma s is equal to delta n infinity over nt. But you know that delta n infinity over nt is equal to 1 over 1 plus I over is, which we have defined in the appendix. This term has been defined earlier in the appendix, and I have also shown you. So comparing these two terms together, we can get e to the power minus gamma t over gamma s is equal to 1 over 1 plus I over is. So the equation number 10 can be written as, so replacing e to the power minus gamma t over gamma s from this equation, we can write equation number 10 as shown, that is alpha is equal to alpha naught over 1 plus I over is. And you see that this is the same relation we have derived earlier for the continuous case. So that is the shape of the absorption line in the pulsed regime, because this is the pulsed case, and here I is the intensity of the pulse regime. So that is the shape of the absorption line in the pulsed regime remains equal to the case of continuous wave when the saturation occurs. So we have discussed, you see that all the parameters all the queries made in the question, that is we have explained the absorption coefficient, that is the saturation behavior of the absorption coefficient for the case of the continuous electromagnetic wave and for the case of the pulse light. And in the pulse light we have discussed the two cases, and we have also obtained the saturation behavior of the absorption coefficient for the two cases of the light pulse, in which the time in which the pulse was much longer, and the other much longer in comparison with the upper state lifetime tau, and the second case when it was much shorter, that is the pulse duration was much shorter in comparison with the tau or the lifetime of the upper state. So all the questions, all the things asked in the questions have been addressed. So this was the appendix, and I have also been referring the equation from the appendix while I was delivering lecture over today's lecture. So this is the end of slide number 59.